So I'm going to ping. Yes, and our second speaker is Todor Tsankov, who will tell us about Gleason complete flows of locally compact groups.
Thanks for the introduction, for the invitation. It's always a pleasure to be back at NET. Okay, so what I'm going to talk about, so everything is joint work with Albertin Lepudec. And then so it is also a talk in topological dynamics, as I suppose all of the talks today. But I'm in a sort of a more general setting. Okay, so I'm not, there are no hidden assumptions. So let's see. So G will be G will be a topological group. And then so the objects that I'm interested in is so continuous actions that G is flow. Okay. So this is just a continuous action on compact space, and this is so it's an action and it is continuous. Okay, and then let me just maybe recall some terminology. So these things they form a category if you want, so their morphisms are just continuous equivariant maps. And then if you have a surjective morphism, so if you have phi from x to y, which is surjective, okay, so we will say that y is a factor of x, or which is the same thing, x is an extension of y. Or then maybe one last definition. So x is minimum if everybody, which is, if you want, this is the same thing as just that there are no flows. Yeah, it's called minimum because this means that it has no, it has no subflow. Yeah, it has no proper subflows. Okay, so now comes sort of the main definition of the talk. So this is what all of this is going to be about. So an extension phi from y irreducible if so every non-empty open set in X, so every X which is not empty open contains a fiber. It contains fiber of fibers y for some phi. So this is, as you see, this definition, it does not depend on the action, right? So this is just a definition of a map between topological spaces. Is it okay?
So it's not. So there's no phi is not a dynamical factor.
Well, it's the definition is for any just for a continuous map between topological space. But of course, you can apply it in this situation, and then you say that the factor map is also very so okay. So maybe let me just tell you a few things. So if X is metrizable, and this is probably a much more familiar notion. So if X is metrizable. So you see, I'm not making any assumptions on like metrizability of X or anything like this, and this is going to be important in the whole.
Right, what are your assumptions on it?
Compact Hauser. That's all. So if X happens to be metrizable, then this is equivalent. Then so irreducible is equivalent to what is known as almost one-to-one. So almost one-to-one just means that. So if you look at the set of x's, such that phi inverse phi of x is x, so this set is that. So it's automatically a G delta set. Okay? So this set here is automatically a G delta set if x is metrizable. So and then you say it's almost one-to-one if it is also dense. So basically means that on a dense G delta set of x, so the orbit. So if you look at the image, then somehow the fibers are just simple. So to see the equivalence of these things, so it's a nice exercise of using the Baer category theorem. Which if you haven't done it, I will leave you. I leave it to you. And somehow these, I mean, almost one things they. So they're important in dynamics, and they already appeared in the last talk. So maybe I'll just use one example. So if we just take, say, maybe G be equal to the group of integers, we take X be a circle, and then we look at the irrational rotation. Okay, so then we have this. This was the first dynamical system that everyone sees. Then you take one orbit, so maybe this is 0, so you take the orbit at 0. And then what you do is you split, so you take every point in this orbit and then you split it into 2. Then of course, so what, I mean, this set is dense, yeah, I mean, because alpha is irrational, so the set of, I mean, this orbit here is dense. So I took a dense set and I split every point into 2. So this is an extension, right? So this is my X, and then this defines Y in extension of X. So the topology here is clear, right? And just the topology that comes from the circle. I'm going to define it, but I think it comes just from the circular order that you have. So this is an extension, which is, it is almost 1-to-1 because I mean, it's 1-to-1 everywhere except on this orbit where it is 2-to-1. Then everywhere else. So this is sort of the simplest possible thing. So this is an example if you want to create a Sturmian. And somehow one of the things it is used for is, for example, it allows you to study symbolically the irrational rotation, right? Or if you want to have some more general dynamical systems, maybe on some connected spaces and so on, this actually produces a symbolic system. So it allows you, which is almost the same as the original, right? The difference is very small, just orbit. So it allows you to study symbolically somehow connected. So this is one of the things. And then, so you can ask. So what I'm really interested in is universal extensions like this. So some extension which actually captures all of these almost 1-to-1 extensions. So if you want all of these irreducible extensions. So for example, okay, so here I can do it for 1 orbit, I can do it for 2 orbits, for 10, for countably many, and then I'll still get the counter space. But this will clearly not be universal because I mean I can always put 1 more orbit and 1 more and 1 more. So clearly what if I want, I mean just look at this system, so it's quite natural actually to do it for every orbit. Right? So then what I can do it, so you can do this. So I do exactly the same thing. I just take every point in the circle and then I split it into 2. For the topology, it should still be clear, right? So this is just the space that I get is just S1 times E1. So I put the order, the circular order that comes from the order on the circle, and the 0-1 order on the 0-1, and then I topologize using the order. Okay, so this is a compact Hausdorff space, but it is no longer metrizable. Okay, it's actually quite easy to see. So this is, it is not even first counter. Okay, and this clearly, it's a 2-to-1. It is still irreducible. I mean, if you think for a second, if you take an open set somehow in X, it will always contain fiber. It will always contain 2 points next to each other. So this is an example of an irreducible extension, which is not almost 1-to-1 because it is 2-to-1 everywhere. Okay. So it was just, sort of to illustrate sort of the use also of looking at, non-metrizable space. Okay, and so now there is maybe I should say one more thing. So for minimal flows, so if X and Y are minimal, so irreducible is equivalent to what is called highly proximal. And so I'll just say this. But I'm not going to use this. So this is just for people who already know about this. So what is a proximal extension? Okay, so an extension is proximal if you look at, so if you have any finitely many points in a fiber, you can, there is a net of group elements which compresses them to a single point. Yeah, or if you want an element of the Lie semigroup, which just sends all these finitely many points to one. Okay, so highly proximal is a strengthening of this, which means that you take the whole fiber as a closed subset of X. And then in the Vietoris topology, you can compress it. So if you want, there's an element of the Lie semigroup that takes this whole fiber and just squeezes it to a point. Okay, yes.
So there you said X minimal, and there you say what is minimal?
X and Y minimal, yes. So it's the same. X is minimal. This implies that Y is minimal. Yeah. Okay. So if X is minimal, then just those two things are true. Okay, so this is so this is Outlander and Glassner. I mean, they're the first who looked at these things in a dynamical. In dynamical setting, long time ago, I think it was 77. And so the whole point is that instead of looking at almost one-to-one extensions, instead you look at these irreducible extensions. There is actually a massive array. Okay? So among all irreducible extensions, so there is a universal. Okay, which has the obvious universal property. So let me maybe denote it like this. So S here X, which has the obvious universal property. So you have, so of course, this extension is irreducible, and then for any other irreducible extension, you get a map. Yeah, like this. Okay, so this again, so this is again a theorem of Outlander and Glassner for the minimal flows, and it's due to one Zucker in general. And then I mean I'll give you like the different construction. I mean just in a second. And then okay, so maybe I should say one more thing. So this is so this is something that you can associate to every flow F, and then it also defines an equivalence relation on flows. Right? So what is the equivalence relation? Is that they have a common irreducible extension. Right? So having a common one, this defines an equivalence relation, or which is the same. I mean, these things are isomorphic. Right? If you can declare X to be equivalent to Y, just if SG of X and SG of Y are isomorphic as flows. Okay, so this splits the somehow all flows into these classes, sort of highly irreducibly equivalent things. And then each class has a distinguished element which sits on the top, which is this thing here. Okay, and somehow the whole point of this talk, I'm try to convince you that these things are actually interesting to look at, and they satisfy nice properties, which most flows do not satisfy. And we have just we have one example of this, but I think it is worthwhile. So now let me tell you what is okay, and we'll call it Gleason complete. Okay, so this is the thing from the title. So X is Gleason complete. If SG of X is already equal to X, so it admits no proper highly proximal extension. And of course, this thing is idempotent. Yeah? So if you apply it twice, of course, you get the same thing. So this. So now let me tell you. So maybe I'll tell you why we call it like this. So what happens if G is discrete? So if G is discrete, the things are very simple. So if discrete, well then this SG of X actually does not depend on G at all. Okay, it just depends on the topological space X, and I'm just going to define it. So you look at the Boolean algebra. So of it's called R(O)X. So this is the regular O concept. So regular O concept. X. Regular. So O concept is regular if it is equal to the interior flow. Right. So something like this is not regular. Yeah, it's like a disk, and then you remove this point in the middle. It is not a regular concept because when you take the closure and take the interior, you get the point back. And so this is a Boolean algebra. So so what is the point? So the intersection is the intersection, and the complement is just the interior. And of course, you take the complement of an open set, it's going to be closed, and then to get back an open set, you just take the interior of that. Okay. And so it's easy to see that this defines Boolean algebra. And then what you can do is you can define so X hat just be the stone dual. Okay, so this is sometimes called the Gleason cover of the space. So of course you have a map like this. So the map, okay, we're just going to say what the map is. So what is the stone dual is just an ultra filter on the Boolean algebra. Well, so if you have a ultrafuter here, what you do? You just look at all of these regular open sets which are in the ultrafuter. You take the closures, you take the intersection. It's a singleton. It gives endpoints. Okay, so it's a very natural. It's a very natural thing. I mean, if you think for a second, and then what? And this map is irreducible. Okay, so this map is irreducible, and this has this universal property. And all of this was proved by Gleason in the early 50s. So here, notice that there's no group. Yeah, there is. I mean, this is entirely a topological construction, and the group somehow does not fit. And okay, so and why? Where did the word complete come from? So you see, this algebra it has the property. This R O of X. It has the property. This is a complete Boolean algebra. Complete. So what does this mean? Complete just means that every subset has a supremum. So if you take any subset of the Boolean algebra, there is a has a supremum, you know, in the usual sense of like partial orders. So in the if you pass to the dual, so what is the supremum? So then this completeness it corresponds here to what is called an extremely disconnected space. So this is a bit of a weird property for a topological space. I mean, if you haven't seen it before, it means that the closure of every open set is open. Okay, and then what is this? What is the relation to completeness? Is that so what is the if you have a Boolean algebra? So what is the Boolean algebra of clopin sets? So what is the supremum? Well, we take the union, but of course the union is not clopin. Yeah, it's just open. Well, but now we take the closure, and it becomes clopin by this property, and now this is the supremum. Okay, so it is not. It's a very natural. And of course, these spaces are never metrizable. Yeah. An extremely disconnected space is metrizable if and only if it is finite. Okay. So now maybe let me. So actually, when did I start? According to this clock.
7 past.
Okay. Thanks. All right. So now let me.
That's not important. You can speak until 52.
Okay.
Independently of when you start.
Huh? Oh, they become so the regular open sets of X. They become the clopin set here because this is what stone duality is. Right? It starts with a Boolean algebra. It produces a zero-dimensional space such that you realize the Boolean algebra as the Boolean algebra of clopin sets of this space. There's any other questions? Okay, so now let's. So of course, if now G is a topological group. Yes, of a discrete space, spaces. So yes, so if you have say beta n is an extremely disconnected space. I mean, this is different from the fact so beta n is what? Beta n is the stone space of the Boolean algebra of subsets of n. And of course, all subsets of n. Of course, this is of course a complete Boolean algebra, right? Because we just take the union of, I mean, to have a supremum, you just take the union of all sets, so this gives a supremum. So yeah, this is like an important example of an extremely disconnected space. I should say have said one important thing, which well I forgot to say, but I can say it now. So another point of these extensions, these irreducible extensions, is they preserve all sorts of dynamical properties. So they preserve minimality, for example. They preserve proximality. They preserve strong proximality. Whatever. I mean, so most dynamical properties that you can think of that can be expressed in this way, they're preserved by these extensions. Okay, and this also gives you. I mean, it also gives you examples of flows like this, but maybe I'll say this. Okay, so now here's a topological group. I mean, of course, I can do exactly the same construction as before. And I'll have, I have G acts on X, and because everything is so functorial and so nice, G, of course, will also act on this X hat. And this is obvious because it acts on the regular open sets.
Is the maximum the continuous factor?
Yes, this is a proximal extension. So. Okay. Right. So of course you get an action here, but now of course there's absolutely no reason if you have a topology on G. There's clearly no reason for this action to be continuous here, right? I mean, if you think for a second, for example, if G is a connected group like the reals, and then you do this, of course, this X hat is always a zero-dimensional space. But of course, if you have a a minimal action of the reals, I mean, the space can better be connected. So this clearly is this action cannot be continuous in general. There is no reason. Okay, so then there is sort of a trick how to deal with this is to take, if you want, the continuous part of the action, whatever this means. So I'm going to try to explain this. So there are basically two approaches for constructing this object. Yeah, so one of them is what Andy Zucker did. So he just looked at the same Boolean algebra, but instead of looking at all ultrafilters, he looked at near ultrafilters, whatever they are, and then which are defined using the topology of G. And then this turns out to work. So I'm going to explain a slightly different method, which changes. I mean, then we take a real dual, but of a more complicated object than a Boolean algebra. Okay, so we look at a real algebra, and then we take the dual of that. Okay, so let's say this quickly. Let's see. So this algebra of regular open set. So another way to look at it is you can just look at all Borel sets, and you can divide by the meters. Okay, so meager is in the set of bare category. Yeah, this means that so a set is meager if it is included in a countable union of nowhere densities. And so okay, this is an ideal, of course, in the Borel sets. I mean, this is a Boolean algebra. It's an ideal, take the quotient, and it's the general fact that this algebra is the same as this one. But now there is a way to actually generalize this. So instead of looking at Borel sets, you can look at Borel functions. So you can look at bounded Borel functions. And then again, you have to divide by this ideal. So you just divide by functions. So real value, yeah, Borel, I mean real value functions. Okay. So you divide by functions which are zero on a Omega set. Okay, zero on Omega set. Okay, so this is this is an algebra. It's a real algebra, and this is an ideal. So you just can divide by this and you get another algebra. It has a norm, yeah. So this is I mean, very nice algebra with a norm, and it's a Banach algebra. All of this, and then you can take. So there's a dual. Okay, so you can take the dual of this. So the dual is just all homomorphisms from this to the reals. I mean, if you want all multiplicative homomorphisms from this to the reals. So this is a dual. It's a compact space, and of course you get back this space there. Okay, this is not very simple. So X hat is equal to the dual of this thing here. But now, okay, so it doesn't look like we did much. Okay, we got the same object back. But now we can actually look at this if you want this continuous part. So we can look at the part of this algebra where the action is actually continuous. Okay. So this. So we define BG of X, be O F E of X, such that the map that goes from G F so what is the say what the topology is? So this is in G, of course. And then F. So what is? I mean, here we have a norm, right? So this BG of X. So the norm is. So here we have the sup norm on this. Okay, so here we have the sup norm. And then okay, you just divide by some ideal. So you also, I mean, it's a closed ideal. So you also get a norm on the quote. So another way to look at this is if you just have a Borel function, you can define the norm just as the essential supremum. The essential supremum with respect to this idea. Okay, so the norm is bigger than R if F is bigger than R on a non-meager set. You can write this down. So the norm of F is bigger than R if the norm is this is bigger than R on a non-meager set. And in the same way that you define, the normal L infinity or things like this, but there it is with respect to the back measure. I mean, to null sets, and here you use the ideal of meager sets. I mean, you can define this for any sigma ideal. It will give you a norm. And now, okay, so now this is, if you want to, we just chose the elements of the B of x where the action is actually continuous, right? Because I just put the, the f for which the action is continuous, and I put them there. And and so the theorem, if you want, is that this thing SG of x, the dual. So this again, it's easy to see that this algebra is closed in this topology. So it's again, it's a nice algebra. You can take the dual against all homomorphisms to the reals, and then this is one way to recover this. Okay. So again, there are two ways. So either you look at the Boolean algebra and then you look at near root recruiters, or you look at this real valued algebra and then this real algebra and then you take the dual, but then you have to pass to a subset of the algebra so that to ensure that the action is continuous. All right. So maybe if so if you got lost or if you don't like it, I mean now it's time to wake up again because I'm going to switch topics. I mean, this was just a construction of the object that I sort of care about. But now we can just.
You can't take 0-1 valued functions.
Put me 0,
You
1
really need to put real.
Yes, because there is no way. I mean, if I look at if it's a Boolean algebra, the dual of Boolean algebra is always a zero-dimensional space. So it is not possible to get a connected space. So you have to do something like this, yeah? I mean, if you want, okay, so one way to maybe convince you that this actually makes some sense is, so what is a way to produce an almost one-to-one extension, or say in the metrizable case? So you start with your system, and then maybe there is some function which is, you really like it to be continuous, but it is not. It's only semi-continuous. But then you can just declare this function to be continuous, and this defines an almost one-to-one extension. But if you want to have a closed set that you really want it to be open, okay, you declare the set to be open and defines an extension. If you do this with only countably many sets, you get a metrizable system. But if you do it with uncountably many sets, you will get a system which is not metrizable. But this is somehow how all of these things work. I mean, this almost one-to-one thing, which just corresponds to different subalgebras. Here I just take all of them, but I can just take some of them, and this will define the intermediate extensions. I mean, for example, in the Sturmian example, I mean, if I just take, this set here, I mean, this interval here, and I really want it to be, I mean, maybe I take a closed interval and I really want it to be open. And then I declare it to be open, and this defines me this extension. See, this is one way to see this. All right. So now so from now G is going to be locally compact. Okay. So from now until the end of the talk. So this was completely general for like any topological group, no assumptions whatsoever. But now I want G to be locally compact. And then I'm going to look at the following thing. So let me know by f of G the closed subset. Closed. So there is a topology on this thing. So this is called the Chomsky topology. So topology. So there are two types of open sets. So there is, you look at all closed sets which intersect some open set. Okay, so I look at OF. So I look at OF, which are closed, which intersect some open set. So I declare this collection to be open. So this is one. And then the second one, I take some compact set. And I look at OFs, which are disjoint from this. And I also declare this to be open. Okay, so these are two types of open sets. So these two things, they define a topology, which is, it's a very nice topology. Yeah. So if G is second countable, this is a metrizable topology. Okay, so it's always Hausdorff. And then if G is second countable, this is metrizable. So it's a very nice thing. So if G is discrete, this is just the the pointwise. I mean, this is just the topology on 2G, the topology, the product topology. But it works for any locally compact space. Okay, so now what I care about is the collection of subgroups in G. Okay. So this, of course, it's a subset. Yeah. The subgroups. which with A. Those happen to be a subgroup. So this is a closed set. This is a closed condition. So this is a compact set. And it's also a dynamical system. Of course, G acts on this thing by conjugation. And this, I think it is very important in group theory. Actually, now quite a lot of people do look at this and trying to see what the space is and trying to understand the subgroups and so on. But it's also important in dynamics for mostly one reason. That if you have any dynamical system, so if you have V X, so there is a very natural map, that you just send X. Let's call this. So this is a stabilizer. And you just take X and then you send it to the stabilizer. So the map goes from X to the subgroups of G. And so this you can see that a lot. So especially in the measure theoretic setting. Because there this is a nice, for this is always a measurable map. And then maybe if you have some kind of measurable dynamic here, you get an invariant measure here, and these are called IRSs, and people classify them and study them. So you can also do it in the topological system. But then there is a problem. So the problem is that this map is not continuous. Okay? So start. So it is semi-continuous, but not continuous in general. Okay, so what the semi-continuous means, you have two types of open sets, like this and this. So semi-continuous means it's either lower or upper, depending on how you want to define this, but so it's semi-continuous in the sense that if you take a pre-image of this type of open set, it is going to be open in X. This is always going to be true because this K is compact, so that you can force convergence and so on. But for this, there is just no reason. And in general, it's just not.
So semi-continuous means for half the open sets.
Semi-continuous means for half the open sets, but then you have to choose whether you call it lower or upper, and I never know. Yeah, the notion of semi-continuity always makes sense when you have two different types of open sets. And then all right, maybe now state the main theorem of the talk, and then maybe I'll try to convince you. Okay, so here is the theorem is very simple. That if so G is locally compact. So this is a flow, and it is how do we call it? Gleason complete. Okay, Gleason complete. So I just remind you, this just means that it has no proper irreducible extensions. Or if you want, it is the maximum irreducible extension of some. And then the conclusion is that the stabilizer map that goes from X to subgroups of G is actually continuous. But it's a funny statement. It's not. Okay, so some map is continuous. So maybe the first thing to try to convince you that the theorem is non-trivial. Okay? Because it's not very often that continuity of some map is actually proven.
So what's the requirement for G? What are the requirements for G?
Locally compact. What is written? There are no further requirements, so it is true for any locally compact. All right, so let me look. Maybe I can tell you a couple of corollaries of this, which were actually known before. So first one is it's the theorem of Froelich, which is that if X is extremely disconnected and G is a homomorphism of X, then the set of fixed points of G, so the set of X is such that Gx is equal to X, is over. Okay. So it is not a very difficult theorem, but I think it is definitely not trivial. Okay? So if you start, you can try to think how to prove it. There is one idea, but there is an idea. You have to do something. So this is just equivalent to this theorem for discrete groups. So if G is discrete, this is just equivalent to this. If you just write down what it means, just do the same. Okay, so here's another one. So this one is due to each. And it says that every locally compact group admits a free flow. Free just means that every orbit is injected. I mean, all sublevels are free. So how do you get that? So what you do is you look at what is called this Samuel compactification of P. So this is Samuel compactification. G, which is the same thing as just the dual of the right uniformly continuous bounded functions. I mean, doesn't matter. Okay, some algebra functions. Look at the dual, and then it's some complex space, which is this Samuel compactification. Okay, so this is completely constructed by Samuel a long time ago. So this works for any uniform space. Yeah, there is no. And of course, so this G is always embedded here. So this is it's a compactification. So of course, a point in G is an element of the dual. I mean, if you have some algebra functions on G, evaluation at a point is most certainly a homomorphism to the rings. So this gives an embedding of G here. It is dense. And then we have this action. So of course, G acts on itself by translation. And here, most certainly, the stabilizer of any point here is trivial. Yeah, because it's just the action of G by itself on itself by less translation. So of course, so the stabilizer is trivial, but this is dense. So if the stabilizer is trivial on a dense set, but then the map is continuous, so it is it's trivial everywhere. Okay, which shows that the action is trivial. Any questions?
So why right? Why right?
Because I want the action, because I act on the left. Okay, so my G times F is F. So here I act on the left, and what I want this map to be norm continuous. Yeah, I want the map from G to the orbit of G times F to be norm continuous. And this is exactly the same as this function being right equal. That left translation is. Doesn't matter. I mean, half of the people call it left, the other half call it right, but it doesn't matter. But it depends on the side on which you're acting. So if you want, if you have a right action, so if you act on, if your flows are on the right, then you have to look at left. Okay, so one more application. So these URSs. So this is a uniformly recurrent subgroup. Subgroup. So this is just by definition is just a minimal subflow. Minimal subflow of the subgroup sub G. So you look at all. By conjugation, you act on the subgroup by conjugation. You just look at the minimal flows. There are probably a lot of them. I mean, there are fixed points, like the normal subgroups are fixed points, but then maybe you have some interesting minimums. So of course, subgroups of finite index, they give you finite subflows, which are URSs, also not very interesting. But sometimes there are ones which are actually interesting. And then, so this is defined by Grassner and Price. And the reason they define it is there is actually, there is a way. I mean, even though it's not here, it's not continuous in general. So there is a way to define a URS that corresponds to dynamical system. Okay. So if you have some dynamical system X, then you can, let's call it maybe alpha. You can define the URS of alpha. Well, it's a bit complicated, right? What you want to do is just take the image of X by the stabilizer. But the map is not continuous, so it's not going to be compact. But what they proved is that So, okay, you take the image, the stabilizer map, which is here. You take its closure. Now it's a compact set. And now, so they proved it has a unique minimal subflow. Okay, so this is the unique minimal subflow of this. Okay, and this is the definition. Which, when you see it for the first time, I mean, it is not extremely convincing why this definition is, relevant and why it is the correct thing and so on. Which, I mean, after you spend some time with it, you realize that, I mean, they define the right thing, being left and right. But so now what I'm going to suggest is an alternative definition, this, which of course gives the same outcome. But I somehow find it more, aesthetically pleasing. So what do you do? Well, so you start with your X. You go to its maximum, whatever, the universal irreducible extension. And now, we look at the stabilizer map here. Oh, now you're in the correct category, right? Because this map is actually continuous. And of course, it's G equivalent. This I didn't say, but this is obvious. Yeah, the stabilizer map is G equivalent, so if 2 points are in the same orbit, here the groups are continuous. Or then you take the image of this. Right? I mean, and I'll just take the factor that you get. And well, you get the same object. Yeah, whether you do this or you do that, it is the same. So this is, so on the one hand, it is more aesthetically pleasing. But it also has another practical advantage that now the minimality assumption on X somehow disappeared. You can do this for any flow X at all. You start with any flow X, you do this, and then you take this, and then now you have this stabilizer flow here, which is associated to the. Is it time? I think according to this, I have like 3 more minutes.
No.
Maybe some session, maybe
Something.
Okay. Right. So you can do this with any flow which is not necessarily. And of course, this definition here, because of its nature, somehow it does not work for non-minimum flows because you look at the unique minimum subflow. Okay, so this is that. And then for one final thing is so there, I mean, you can ask, what are these flows? I mean, this, okay, there can be abstractly constructed like this. I mean, the Gleason complete flows. But all universal flows with some properties. So if you have for every group G, there is something called the universal minimal flow, which is just universal for all minimal flows, but it admits a map to all minimal flows. So of course it will be, it has no extensions whatsoever. So of course it will be Gleason complete. So another one is the universal proximal flow, because it admits no proper proximal extensions, but I mean, it's highly proximal implies proximal. So again, this is one of these, and maybe like the most famous one and important group theory is the first member boundary. The first member boundary of G. So this is just the universal strongly proximal, which I'm not going to define. Strongly proximal. And well, so for the same reason, this one is also Gleason complete. So in particular, we get something which I think was open and some people were interested in for like reasons of fixed simplicity and things like this. Is that if the first member boundary is essentially free, then it's actually free. Right? So it just follows from this. So of course, in particular, this continuity of the stabilizer map. So it implies that if you have a flow which is essentially free, it's just the same as free. Right? So you get this. I mean, this is, for example, what I did here for this. This flow here is essentially free, and I just applied the theorem. So I think this is good time to start.
Thank you very much. Some questions or comments?
Where do you use exactly the G in the combine?
Oh, interesting. So this subgroup of G, the set. I mean, this primitive one. So you can define it for anything, but it is Hausdorff. You can only include it. So otherwise, you get a non-Hausdorff. Of course, you're using the proof, but so the notion about URS for non-locally compact group is not to understand. I mean, I'd be very interested if, there is something like this, and so I'm very interested in non-locally compact groups. But for the moment, I mean, this topology does not, it's not Hilbert topology, so we go out of this category. So if you think for a second, I mean, how do you separate two open sets? I mean, so if you think, if you have two different open sets, how do you separate them? I mean, you need local compactness, and you need these two things to talk to each other. I mean, the intersecting open and being distant.
There, the corner for which you took the universal extent of the Samuel complexification.
Oh, sorry, the Samuel complexification, it already is, it's one of these universal things.
Yeah.
So it is, actually, so the Samuel complexification of anything is Gleason.
Could you say again which is the application to the first comparison?
Yeah, so if the first order boundary is essentially free, then it's actually free. So the way this is used, of course, no one knows what the first order boundary is. But if you can just produce one boundary, so if you can produce one strongly proximal flow, which is essentially free, which is using memorizable, not something that you control and so on, then automatically you know that the actual abstract object.
So if there are no more questions, I have an announcement, which is that we have a coffee break till 16:15, and we have lots of chocolate for the coffee break. So don't move, and let's thank again the speaker.